Okay, welcome back. How are you doing? Welcome, Prince. How are you doing? Welcome back, everyone. Hopefully, everyone got a chance to quickly review whatever we've discussed on Monday. I finished it in the points in the lecture, in the slide that I told you the impact of resolution on analog to digital conversion. I'm going to pick up from there. And let me summarize what's the plan for today first. This is some kids that come in. Okay, today I don't load you with too much of theory. I'm going to spend somehow the rest of the class on solving problems for you and showing you in case that you have, like, for example, examples, if you are in the learning environment, right, like whatever we are doing in here, how do you calculate analog to digital conversion? How do you calculate resolution and stuff? And then in case you're an engineer later in any company, you are expected to design some microcontroller, some sensor and stuff, still this information are 100% beneficial and requirement for that. So let's start with, but before that, while I'm just bringing up the screen, is there anyone who has some question for me? Any question from the yes? In the OneNote?
Are you posting the videos in the OneNote?
Anything I'm typing for you in here, video, sure. For sure, video will be posted, and I already even announced. Have you ever had the chance to look at my announcement? Not today. I didn't do it today, but I'm going to share my screen right now. Give me a sec. And even I've already clarified every single lecture this semester I'm teaching for you, as I know you need some reference. Look at here. This is my announcement yesterday. I even included all of the links for you. Also, that's going to be your job to go there and check what do you have under Avenue. Look at here. I'm not going to do the same. I just did it one time to make sure everyone knows what you have. But for upcoming lectures, also for the rest of the semester, these are the weekly module. If you expand them right underneath every single PDF that you have as a lecture slide, you can see another option, which is my recording. If you click on it, if you click on open link, it's going to send you to YouTube, and you can see it in there. Reason why YouTube? Simply because videos are long. It's not easy to upload them to Avenue. Avenue is not accepting them. Okay. The only reason behind putting these videos on YouTube is that one. I cannot upload them to Avenue, right? Size is huge, right? So you can simply go there, watch them, and for every other one like that, we can see underneath, and these are fresh recordings from this semester. And this is the one from Monday, and I'm gonna write after that, since the analog to digital is a longer and more detailed lecture, I'm gonna put another one under the same lecture slide. So even all of this solution in class problems that I'm doing, he's asking for my OneNote or my written version. You don't even need my OneNote. Also, you have it inside my recording. Look at here, I typed it in a very nice, neat format, solution to every single example. Look at here, much better than my handwriting, okay? I already spent time, typed right in here, you can find them. How about that? But just you need to maybe sometime do some efforts, have a trip here to the Avenue, and come see what I have in there for you. I'm going to continue with, this is exactly where I have left the previous session. I'm going to pick up right from there. That was the only question, right? Can I get access to this source or no? Was the only question, or still you have more questions? If anything more, let me know before I start. Kids, while I'm just creating another, I already did one, but for some reason, OneNote is not always updated. It takes some time. I already created another one in here. So I'm gonna do it again. So from here, we are going to continue on solving more problem. So first thing is this one. Who can tell me what's the impact of resolution on converting analog to digital? Yes, please.
Is it more samples?
More, why we need more sample? That's 100% correct, but why?
Get more information about curve?
Resolution. More samples means
Better.
higher resolution. Somehow the answer is inside the question. If I need more sample, that will help me to have a better resolution, a higher resolution. How about that? So look at here. In this example, for some reason, this guy is not interacting. I'm going to connect it to the PC directly. Hopefully I can write, yeah. So look at here in this example, last session, I told you, if I'm having 2 bits resolution, starting, suppose from 0, 0, how many interval I have? I'm going to go through, because my maximum in this point is like 5. All I need, if it is a 2-bit, all I have is 2 to the power of 2. I'm going to quickly review resolution because I need it again for the next example. Please pay attention and learn these examples today. Next week, I'm going to quiz you from the same examples. I'll get you to solve it yourself. So this quiz is not going to be closed, it's not going to be open book. So learn how do I solve it, and then I give you only one question, only one, not more. It takes only 10 to 15, maybe 10 minutes or 15 minutes, something like that. Just do exactly what I'm doing right in here, okay? So let me summarize one more time for you kids. What is the resolution? In order to calculate resolution, you need a reference voltage. But what is reference voltage? Reference voltage is always the maximum voltage that you have available for that system. I'm going to say like this. First, if you are looking at a step size, pay attention. And if you need to have your own written version, you are more than welcome to do so. So if you want a step size, simply you need to have reference voltage, Vref, and I'm going to call this part N, standing for level size. I'm going to see how do I calculate each of these sizes. Each of this, let's say, is a level, and I'm going to calculate the size for them. How do I do that? So I put the N in here. Now I'm going to say this is my level size. How do I calculate it? This level size is 2 to the power of N. What is N? Who can tell me? Number of, this is number of bits. Number of bits here in learning environments, I'll give it to you. And of course, this is exactly what impacts the resolution of my system. If I'm having more bits, means I'm having more level to go through, right? Therefore, if I have more level to go through, for example, in here, I'm having only 1, 2, 3, 4 of them. How many I have in here? I have more than that because in here my bit is 3. But in here my bit is 2. Here I start from 2 bits. Here I start from 3 bits. If I have 3 bits, I have to go through more steps. Makes sense so far? And then if I'm going through more steps, means I'm coming closer to that initial digital wave or digital signal. Makes sense so far, kids? Why we do this? Now, I have most of this. How about Vref? Remember I said reference voltage is a factor of your V, you can say RH minus RL. What is this two? RH is higher voltage. I'm gonna write them down for you. This is your higher voltage. And this is your lower voltage, right? So now you have a good understanding of all the terms that I have in this equation. If no, let me know, I'll go through it again. So keep this in mind. if I'm gonna have a better system with higher resolution, of course I need more bits. Remember in the lab I said our microcontroller is a 10 bits resolution, not register, 10 bits resolution, but still we can set it to 8 as well. And all of you practice that, right? So then when you had it in 10 bits resolution, you were able to come closer to the input voltage. That's why you could turn on that RGB on the corner as well. While you had it on on 8-bit resolution inside the analog to digital function, at the end of the code, it was 8-bit. 8-bit was what? 0x A7. A7, right? That was 8-bit. When you had it set inside the analog to digital function, it was not able to turn on the RGB on the corner. Then you set it to 0x07, it became 10 bits. You had a more accurate voltage, and you were able to not only, for example, use the pots, change the potentiometer, at the same time, RGB interact. Or if you are looking at the temperature sensor, at the same time, RGB will interact with the temperature sensor or the light sensor, right? That's the impact of resolution. Now keep this in mind, and we are going to look at a little bit more advanced example using exactly this understanding, nothing more, nothing more. So I have been given this question to make it more clear. I'm gonna get a copy of this, bring it to here, then I'll close the lecture slide to solve this one for you. So I'll put down this one here. I'm gonna so now what is the question? Question is asking me, I'm having a sensor, and this sensor provide 1 micrometer accuracy. Accuracy is 1 micrometer. So I'm gonna take note. My sensor range is given, my sensor accuracy is given. So my sensor range is what? The range is 0 to 2.5 centimeter. Centimeter, maybe I'm gonna make it easier. I convert it at the same time to meter. So therefore I'm gonna say 0 to 2.5 centimeter to meter. Who can tell me what would be the conversion? 10 to the power of -2. Then this is the only thing that I'm doing in here. I'm converting this one to meter. This is my sensor range. And then I'm having the voltage output right in here. It says your voltage of this sensor is 0 to 10. So I put it, voltage output. This is a good way of calculating, kids. Whenever you have a problem, first summarize your understanding for the given information. The way I do it on the side. That will help you to understand what's the question mark, what you have, what you need to look for, right? So always summarize your understanding like this. So when I say output voltage, it's going to be actually the range. The sensor voltage is going to be 0 to 10. And this is in the unit volt. What does it mean if I'm going to calculate my reference voltage? How do I calculate reference voltage? Yeah.
Would 0 will be your VRL?
100% correct. This is my VRL. Write it down for yourself. Take a note what you have. And this is going to be RH. Now I know what I have in here. Makes sense so far? Next, I'm asked right in here now, this laser sensor can be used to scan moving objects to validate the accuracy of manufactured part with 1 micrometer tolerance. So now I'm having the tolerance, and that's 1 micrometer. So accuracy of this tolerance means this one is talking about my position, my X, right? Therefore, I'm going to say position. I'm going to call it X is 1 micrometer. You can also have your own. At some point, I'm going to calculate what is my delta X. Till now, I know what is that. I'm looking at the, if I want delta X, then I'm looking at my accuracy or precision. Later, I'm gonna look for my precision, which is my accuracy. Now, before that, I'm asked, look at here, find a proper ADC to communicate between the sensor and the microcontroller. Suppose this is my microcontroller, and of course, you know, this is my sensor. So now I'm going to use analog to digital method in order to first look at the position, find the output of the sensor. I do not know still what is my output of this sensor. In order to know the output of this sensor means V out sensor, because this one is not given. I need to figure out what is my precision, which is dx, right? Let's do it together. So I'm going to start with X. Remember, I said X is going to be my position. But before that, kids, voltage output in here has a linear relationship with the position of the object. Suppose that I'm having this object. This is my object. So then in here, the voltage output of the sensor, the V out of the sensor, has a linear relationship like this with the position of this object. Let me draw it in more detail in here. I'm looking for the position. Let's say this is my position. Position of what? Position of this object. And then I'm having a maximum 10 volt. Therefore, I'm going to put in here 10 volt. This is my voltage. So object X is moving. If X is moving in this direction, voltage supposed to start from 0 and maximum reach to 10. Make sense? What's this graph? So I'm going to say this is V out sensor, right? And now from there, I can say X is equal to what was the range? The sensor range is this one. Therefore, I'm going to say 2.5 times, because I already converted to meter, over what? My maximum voltage, which is 10. How about V out sensor? Still, I do not have V out sensor. Therefore, I should say V out sensor. Now, I already know my precision is 1 micrometer. Therefore, I can say I already said I can, instead of that, say delta V out. Then I'm going to look for this one, and I can say delta V out sensor is assigned to, just rearrange it, 10 over 2 to the power 2.5, 10 times 10 to the power of minus 2. And then I have this X, because I'm looking for the difference. Therefore, I make it like delta X. Makes sense? But what can I put down instead of delta X? I already said delta X is going to be 1 micro. So then this one is your 1 micrometer. So if you just calculate this one, it becomes 10. Just put this one in here. I'm gonna just give you the number. It becomes 4 times 10 to the power of minus 4 volts. This is going to be your analog to digital must actually in here provide at least the resolution. Question? This is the position. Suppose this is the X position. I'm going to draw it for you. Suppose this is the X, okay? Position or X. And this is the voltage, okay? And you are going to look at the output voltage of the sensor. X means each of this, right? Because this object each time supposed to move in this direction. Yes, Ella. And I'm explaining it. Okay. If you don't mind, I'm explaining it. Now, I'm looking at what? I'm looking at the first one. Let's say first one is here. This is my first one. So I'm going to call this is my V out at this point. And then let's suppose this one is also your first position. This one. And if this is your first position, this becomes your delta X. Means from here to here, the difference between them becomes your delta X. So far, so good. And the same in here. since you are moving from here to here in terms of position, voltage will change accordingly. Therefore, this one also become your delta, the one I put down in here. Delta V out. Now make sense for everyone? What does that mean, Liam?
Oh, sorry, that's volt at the end.
Pardon?
Volt at the end, right?
Volt at the end? Yes, this is volt at the end. That is volt at the end. This is volt. You got it, Ella? Yeah, you got it also. So now I do have my resolution, and I know that my analog to digital must provide at least the smallest voltage resolution increment. It must be 4 times 10 to the power of -4. And then I can just go ahead and calculate my resolution. If you have a question, just say it.
I understand the delta X, delta V came from. I'm asking how the equation.
This is your understanding as an engineer. I just said it in here. I just said it. This voltage and the position of the sensor should have a linear relationship. Position is changing, voltage is changing. Now you as an engineer to become, if position is changing, which is this one, and you have a maximum voltage, this is your Vmax, maximum voltage, and this is the accuracy, right? Then what would be the output voltage? This is always a standard. This is always a standard equation for you. So output voltage sensor is your, look at here, this is your 10, in here is the voltage, output voltage of the sensor. So this is now, if you don't know now, so this is the output of sensor, maximum. This is the resolution of sensor. This is now an equation. If you want the equation, this is an equation. Output, the difference between the output voltage sensor at its point is gonna be the maximum of the voltage divided by the resolution of the sensor times any change of the location. Now this is the equation, yes.
So the equation is that only for the higher voltage and the higher accuracy range? Only for the higher one? So let's say the higher.
What is this one? I said this is the smallest voltage increment. This is the smallest voltage increment. Means each time, this is the increment.
The equation above it, is that, can we only use that equation when we have the higher voltage value and the higher rate?
Yes.
Can we use it when the lower one is there?
We never start with the low. Most of the time is 0. If you put 0 in here, what?
No, I'm just saying if the higher was like very close. So could this
higher couldn't be variable. Again, engineering understanding. Engineering understanding. First year student, can I have a higher voltage to be a variable? I'm talking about the device. Device is already built. Device is already complete. It's been delivered to me. If the voltage is variable, which kind of device we have with a variable voltage? They always mention all the information. Suppose it's your cell phone. They say, what is the maximum voltage for this cell phone? Have you ever seen any maximum voltage to be variable? It's okay, ask. I mean the depths of the question. No, voltage couldn't be variable. Maximum voltage is always provided by the manufacturer, right? So now I have the smallest voltage increment. Now, how do I calculate resolution? I already gave you the resolution equation. I'm going to write it down again. Resolution, remember it was Vref over, either you can say capital N, then say what is N, which is the size, or simply say 2 to the power of N. One more time, N is the number of bits. Therefore, what should be that? Do I have the number of bits in here? I look at the question. Question is not even giving me the number of bits. Therefore, my question in here is, how do I calculate the number of bits if it is not there? That's the question. Now let's do that part. So what do I have? I have Vref. Vref is 10. And I already calculated this resolution or the voltage, smallest voltage increment. This one is exactly again resolution. I already have the resolution. I already have the voltage reference. Now my question is, what is the number of bits I need in order to get to that maximized or maximum voltage? To get closer. Anyway, this is analog. I'm going to convert it, right, to digital. Which kind of bit I can pick to give me the best resolution? Now I do have the resolution. I'm going to use log in base 2 to calculate this one. Resolution is this, 4 times. It's been given right in here. I put it down. I calculated 4 times. This is my calculation. Resolution is coming from there. So therefore, I'm going to say right now, n greater than log base 2, 2.5 times 10 to the power of 4. So now, even in here, you can put it down. If you want more details, somebody may ask, how did you get into here? Let me just even tell you how I got to this point. In this point, this one was the one that I'm going to find, right? Therefore, I put this right in the side. I rearrange it. And then if you do this one, if you rearrange this one, this, and that's how I found this. This becomes 2.5 times 10 to the power of 4. And then I rearrange it. I rearrange this one. I get this. A little bit of math, right? And now I'm going to calculate it. Log in base 2 to find out what is the minimum value for L. I'm going to find the minimum value for L, for N. Then what do I get in here? If you do like this little, this is base 2. If you do a little bit of math in here, what you get is N greater than 14.6. Now, number of bits for analog to digital must be an integer. Remember, why is that? Who can tell me? Why I cannot have decimal? I found 14.6. We had this in the lab, remember? I have 14.6, but can I have 14.6 bits? This is a decimal point. I cannot do that. Therefore, I have to select a higher integer. This is 4.6. I'm going to select a higher integer, which is going to be 15. So we need to select a 15 bits. I'm going to write it. I have to select a 15 bits analog to digital. For what? To have enough resolution of 1 micrometer. So a 15-bit analog to digital will provide the smallest voltage increment. Now I can calculate that voltage increment because now I do have N. Now I can go back to that to calculate my voltage increment. I'm going to do it right in here. Again, I'm going to look at the resolution. Then I'm going to say, again, Vref, I repeat this part to make sure everyone knows what I am doing. 2 to the power of N. Now I found N is 15. And in here I had 10 divided by 2 to the power of 15. What do I get? Now resolution is going to be 3.05 times minus 4 volts. Make sense? But another question. What if I cannot find a 15-bit analog to digital converter in the market? What would be next? Most of the time, that's not something available in the market, right? The common converters are something like 8 bits, 16 bits, 32 bits, and so on. We don't have every customized number. Therefore, in that situation, these are the common one, 8 bits, 16 bits, or maybe 32 bits, and more. Therefore, if I cannot find exactly this number, my option is go pick the one which is closest to this number in reality. Make sense? Then we have to pick a 16-bit, which is more close to 15 bits in the market. But in terms of calculation, first I have to come to some understanding what would be my number, and then I have to look at market and then find the closest one to that one in the market. So we need to select a 15-bit analog to digital to have the accuracy of, this is a quick summary, to have the accuracy of 1 micrometer. And since it might not be available in the market, I go grab the one which is closest, and that would be the 16-bit. Everyone got it? Taking an opposite or listening? Yeah.
Or when you say the closest one, you mean the closest that's higher, right?
Higher. Higher. Always closest higher. Why not lower? Because higher, I can have still room, but lower, I'm losing something. We always find the closest higher, not lower. Make sense? So now, I'm having another example for you, but before that, quickly, I'm going to put it on the side, minimize it, you review it quickly, capture it in your mind. Do not expect you become expert with only one example. Okay, I already created this. Let me now give you this good understanding in here before moving. Remember, I derived for you. Now, remember I told you this voltage and this position, they do have linear. Now, who can tell me what would be the drawing in here? Let me grab a different color. How do I draw it in here? Because now I do have the output sensor. Suppose right in here. Now I have the V out sensor, and then I do have my X position. This is my X position. Now, if I continue, suppose because I have the increment, I continue and do it for all the increments. Look at here, it's gonna be a linear relationship between the voltage of the sensor and the position of that object, which is moving in front of the sensor. Make sense? So these two are changing exactly at the same time. What was your name? What was your name? I forgot it. Yeah. No, you.
Good job.
Good job. Makes sense. Okay. Everything clear? Okay. Since today class is not very long, we are just with one question almost. So I quickly solve another one for you, which is this one. I've already posted, as I mentioned, posted all of this on Avenue. These two are more important to learn. I just solved this two for you, and the remaining is going to be your work to review them. I'm always available in case you need also extra explanation, come see me. Still, I try to solve as much as possible, and then I quickly introduce op-amp, and I have few more in here that I left them for yourself to try. The rest is whatever I taught you during the lab. So the rest is not, the rest are the lab material for your review. But all I wanted to do is just one more example, a little bit of understanding about op-amp. Because another question is asking, you've got, again, analog to digital. What is this one? It's asking me, suppose that there is a 10-bit. This time I do have the bit. 10 bits in here means which one I have. 10 bits in here means Now I know what is my N. N is given 10 bits. In the other question, I did not have the N, which is the most important factor for resolution. Now I have a 10 bit, and it's asking me, okay, you have also your VRL and VRH, means your voltage is 1 to 4. This is your VRL. This is your VRH. Make sense so far? Now what is next? Next is asking find the corresponding voltage value for your analog to digital conversion. Remember in the other one, you have to look for the bits. Now you want the voltage for the analog to digital conversion. And then for what purpose? Suppose you are expecting 25, 80, and 720. What does that mean? That simply means you are going to design maybe a temperature sensor, and your expectation from the, let me draw it. Suppose you are having a system with your, this is your sensor, but you want to apply some temperature. Remember, very similar to what we do in the lab. The sensor on the side of the setup, if you do not touch it, is reading the room temperature. Almost 23 or something like that. Then I get you to please and kindly hold it, warm it up. That warm it up means change the temperature. And then see if you change the temperature, what would be the binary equivalent on the LED. In there, I show you through the system. In here, I'm going to show you through the mathematical conversion or calculation. If you are applying a temperature, how inside the microcontroller is processed and how you can understand what that temperature is, right? So let's see. Suppose this is your sensor and you are expected to set the T of this one time to 25, next time to 80. I'm going to do 25. You can repeat the same process for 80 and 720. So this temperature for the microcontroller is not understandable as a temperature, right? Remember, it's an analog signal. Temperature is analog signal. Makes sense so far? Therefore, this analog signal must be converted to a voltage, regardless of it is temperature, it is light, it is through potentiometer. Any analog signal is going to be converted to a voltage inside the microcontroller. Therefore, what we have after the sensor is not temperature anymore. For the microcontroller is voltage. So far, so good, kids. Then, what would happen next? From here, this guy, sensor, is sending it to my converter. And then what's the expectation? I'm going to have, remember it was mentioning 10 bits. I'm having a 10 bit. 10 bit means resolution in here is 10 bits. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a 10 bit. Now I'm going to see what would be the voltage through the microcontroller. I'm going to look at the output of the microcontroller. Therefore, how do I calculate? I would say this 10 bit is going to be considered like, let's say this is K. This is 10 bits. This is my K. Because in here, I left you this message. K corresponds to the analog voltage, right? Vk becomes the analog voltage. And then this is the equation. I'm following this exact equation, so I'm writing it down. Vk, this is for always, means the analog voltage, is VRL. It was given, remember, which is 1, plus VRH. It was given, it is 4. I put it down. So far, I'm clear. So it's going to be VRL plus VRH minus again VRL. Again, it was given I put it down. Then times K, right? K is analog digital output divided by 2 to the power of n. N is given, which is 10. So then this is going to be 10, right? Number of bit. N is number of bit minus 1. So now you know now whatever I'm having in here is coming from this equation. This is the equation. Now if you calculate it, for different numbers, this is going to be different. I'm going to do it for V25. Then in here, I have to say V25 to calculate for 25. And then if this is V25, then K in here is going to be 25 over 2 to the power of 10 minus 1. If you calculate this one, what's the answer? Just a little bit of math. It's going to be 1.07 volts. Everyone got the point? Then, if your voltage is if your voltage for 25, if your temperature is 25, inside that 25 will be converted to a voltage, and that voltage is 1.07 volt. Everyone got the point? You got the point? You didn't? What was the question?
It's okay, I'll figure it out.
No, to ask it.
What happens if we pick a different number than 25?
Okay. I said next time you may want to look at 80. If you want 80, then say B80. 1 plus this part is exactly the same. 1 plus 4 minus 1. And then here, instead of 25, put down 80. Everything will stay the same, only I'm going to do it. So now, next, kids. What was your name? Daniel is asking, what if it is a different temperature? I already have another example. So I'm going to look at 80. If it is 80, that's a different temperature. I'm looking for what would be the voltage equivalent of this temperature inside the microcontroller. That's the problem to solve, okay? So then everything in here means all the voltages are the same. I don't change none of them actually. And then just I change the temperature. Now my temperature is 80, 2 to the power of 10 minus 1, right? And then I calculate for 80. If I calculate for 80, it becomes 1.23 volts. Same method. You got it, Daniel? Everyone else got it? Perfect. So then I'm going to leave the 7200. I leave the answer for you. It's very similar. 720, not 7200. 720. If you solve the same thing, it becomes 3.11 volts. Yes. Yes. Midterms, final exam, any assessment, I'll give you the cheat sheet with the equation. You do not need to bring your own cheat sheets. I'll give you the cheat sheet. It's a part of the assessment. Yes, Nicholas.
Why is there a -1?
-1? Calculate for it, Nicholas. This is the equation. Any temperature you are looking for, just put the number down. You got the point?
That's why.
Why what?
Why? How did you get this equation?
How do I did not generate the equation, Nicholas. The equation is a standard equation. Which one was first? Egg or chicken? Somebody tell me, egg or chicken? Why are you asking weird questions, kids, today? It was egg or chicken? Yes.
BK. Is that between the sensor and
BK, that's the equivalence of that inside the microcontroller. Yeah. Kids, I have only a few minutes left. I'm going to quickly explain what is op-amp. And then I have more solved example. Okay, I have more solved example, which is going. Kids, can I have your attention, please? Then I have more solved example for you that is going to be your job to go practice them before next assessment. Bring them to my attention. You are gonna see me next Monday. You are gonna see me next Tuesday. You are gonna see me next Thursday. But next Thursday, I'm going to quiz you. Before next Thursday, review all of this lecture slide. And then anything, come see me. No excuse. Come see me. Okay? Or send me an email. Drop it under the video. Best method. Yes, Ella. One. You are gonna have 2 quiz next week. On Monday, I'll quiz you with multiple choices question as always. On Thursday, I'm gonna quiz you with 1 written problem. It takes only 5 to 10 minutes to write it down and upload it. That's it. Kids, let me finish this one. I don't call it question at this point because I have one thing to finish. After the class, I'm available. Okay? So I'm gonna look at this one quickly in case you haven't heard about op-amp before. What is op-amp? Any idea? What is op-amp? Op-amp is a system, or I would say is a device which is going to help to amplify voltage, current, power, any of them, especially when we are working with analog to digital. And we need to boost either of this, right? Therefore, we need the op-amp. This is the general format of op-amp. We always have V plus, V minus. And these two are the one connected to the source. You may see it for different manufacturer is labeled differently. And I myself seen even sometime for the same manufacturer, they do label it differently. That doesn't really matter. The only thing that matters about op-amp, always you have 2 input, 1 output, regardless of how they label it, right? Always 2 inputs. And the first one connected to positive, we call it non-inverting. And this is inverting, right? That's the standard format of the op-amp. So now you know op-amp is a device that we usually use it in order to somehow boost or somehow amplify the voltage or the power or the current, any of them. So now there is a general voltage, general equation in case we are going to have a closed loop gain for the non-inverting. Now, you know, when I say non-inverting, what does that mean? I already also summarized this one in another document in case somebody needs more detail, and I uploaded on Avenue. You can see it in there as well. I'm going to go quickly show you. Right in here, in addition to everything. So I have one review, sample, and hold. Okay. This is the recording, but I have this review of sample and hold, and I have more explanation about all those solve examples, which I just said right in here, in case you want more detail. So now, when I say closed loop, I'm looking at this part. Since my input voltage in this closed loop, why I say non-inverting? Again, I say non-inverting because my input voltage is going through the positive. If the input voltage is going through the positive, I call it non-inverting op-amp. And I call it closed loop simply because I'm having 2 resistors in here. These 2 are going to be the one that it is boosting the voltage. They are converting resistance to voltage. Therefore, my output voltage is going to be amplified. Now, makes sense? And that's what we call it. If I have input going from here, input, and then I have something like this, which is going to boost, then I call this system gain. And gain, usually the symbol for gain is A. And then that's the situation that I'm having a different output voltage. And the relationship between output and input, then it's going to be, how do I calculate it? My V out is going to be my V in times my gain. My V in times my gain. Make sense? Now, what is this gain? What is this V? Who can tell? This V, look at here, I have Vs plus, Vs minus. Therefore, I can substitute for the non-inverting. Then I can say V out is going to be my gain, and V in is going to be Vs. S stand for, I said it in here and write it, source. Vs, S stand for source. Vs positive minus Vs negative. Now, this is a closed loop gain. what I have in here. I'm going to quickly draw this one, and then, so if I have, let's say, my V in going, just to simplify this one, I have it in here, but usually kids learn better when I explain it. So this is my op amp. I'm going to look at here. Then I'm going to look at my output to be here. And since my V in is going through this pin, it's going to be non-inverting. Here is positive, here is negative. If it is going from this part, it's going to be non-inverting. This one is inverting. This one is non-inverting. Remember this one. And then if I'm going to draw the equivalent of this circuit to make it easy for you to understand, this is Vref, RF. I put it down in here. This is RF. And then this one has a series connection with the other one. And then these two are going to be connected in here. This is going to be my RG, right? G stands for ground resistor. F is your reference. So this means ground resistor, and therefore I'm going to ground here. So this is what a non-inverting op amp is, and the gain you can calculate it like this. I've got a few more examples of different maybe shape of the same system. You can look at them in here, and everything else I already explained it, all of this during the lab time. This is just for your review. Make sure review them, okay? Next class is waiting. I'm going to close. Anyone who has a question, come see me out of the class.